it's sort of like a double bill today, right? So it's a little bit of me, a little bit of you, and let's see how far we get. Now, the part that I'm going to contribute today is going to be somewhat light. I fully understand that you have a midterm coming up. I unfortunately cannot just shake away this one particular hour and not give you anything, because then the amount of hours that we have for the total course is going to be a little too little. So I'm going to tell you only a small step, and I think that's a good compromise.
Small step.
So let's get started immediately. I did mention during the tutorial last week what it is that we're going to do this week. Do you remember what that was? It was a throwaway comments. Do not feel guilty for not having remembered it, okay? But maybe you might have remembered it. Maybe we'll go one step back. What have we done up till now when we went to curved space-times? Why did we go to curved space-times? Maybe that's a better question to ask.
Because all masses move in these curved spacetimes.
Yes.
In the same way.
In the same way, right? The experiment tells you that things all fall in exactly the same way if they are moving only on the influence of gravity. And as a result, Einstein inferred, well, that means that you might as well describe the way that they fall as if they are falling on some kind of curved space-time. So that is certainly one thing that we have done. We've also looked at the description of curved space-time, agreed? So that you know how you can calculate things in a curved space-time, and even how you can calculate exactly how space-time is curved. So what we're going to do today, this was this throwaway remark that I made at the end of the last tutorial, is we're going to connect these two things to each other. We're going to talk about, if you know how space-time is curved, then how do things move under gravity? We know that the curvature has something to do with gravity. How does that curvature look? That's the idea. Now, I hope you understand that if I have a curved space-time and I let things move on that curved space-time, there's really many ways that things can move on that curved space-time, agreed? Let me draw you a picture. One space-time that we looked at, one space I should say. Oh, okay, good. Somebody left their full package of markers here. There we go. Oh. Here's a space-time that was curved that we have looked at. The surface of a sphere. Now, we talked about how you can calculate, how you can go from point A to some point B, how you can calculate how many meters that is, agreed? You take your metric tensor, you construct a line element, a ds from this, and you integrate this ds, and then you have to supply to your integration how exactly you're going to walk from A to B. You don't have to just specify where A is and where B is, you also have to specify how you're going to make that path towards there. To make that very explicit, the amount of distance from here to there, let's call that s, is just the integral of small s. Small s, as you know, ds, is just going to be very abstract here for a second. Is this expression? Is the square root of your line element. We've written down what this looks like in case of a spherical thing, right? Check your tutorials how this is written down. In order to do this calculation, what you typically did was maybe you take a dt out, or one of the dx's out, right? One of your coordinates you could take out. So maybe you take the dx mu out, and this becomes dx mu. These are things that we have done, right? Now, in order to do this calculation, to actually get this number, you have to supply how this thing depends on that thing, what that function is. This is another way of saying visually how you go from here to there. Going from A to B in this particular path is a different function of this x as a function of that x than it is if you would have gone in some other motion. So at this point, just knowing how to calculate how many meters from A to B hasn't really specified yet how you actually go from A to B. So we're missing information here at this point. What we have here is that you can go from A to B on a curved space-time that has something to do with gravity, but the question is which of these two paths, if any, or maybe some third or fourth one, which is the one that gravity actually takes? That is the question. Okay? Now that is the question that I want to answer with you. And it will result in a particular equation that I wrote down in our very first lecture. It's called the geodesic equation. That equation, unfortunately, is well, make it sound any better than it is a difficult equation. In fact, let me already skip to the end and write down the equation. This is the equation we will use in the next 3 lectures when we're going to apply it to black holes, gravitational waves, and to the universe as a whole. So, let's pretend that we did all the math, and let me give you the outcome. You might have written this down in your first lecture. Here's the first one, the first step. Okay, that looks kind of benign, right? It's not that bad. It's only 2 terms. Or is it? How many terms is this? Terms, not how many equations. How many terms is this? Let me ask one smaller question, a step-up question. How many contractions do you have?
2.
2. Okay, so how many values can each contraction? How many terms does each contraction contribute? 4. Okay, so you have 2 of these. So how many terms in total? It was either 8 or 16, so which one is it?
16.
It's 16, right? For each of the values in the contraction over alpha, you still have 4 terms to go for the beta. And since you have 4 of these alphas, and each comes with 4 betas, you get in total 16 terms. So this is an equation that has 17 terms in total. That's 1. How many equations are here?
4.
That's 4. For every view, there's 1 equation. There's really nothing we can do about this. Nature has decided that this is how things move in gravity. So these are 4 equations. Each with 17 terms. You might recall this from our first lecture when I already sort of introduced where we were going ultimately. These 4 equations are, as they are called, coupled. They're coupled equations. You know what coupled means in a mathematical sense of the word?
In each one of them there is a correlation to another, or it's a function of the other, if you wish. I don't know how to say. Yeah. They're not independent.
They're not independent. These 4 equations rely on each other. In order to solve one of the 4, you need the solution to one of the other 3. But of course, that one of the other 3 needed a solution from yet the other 3. And that one needed the solutions to the other 3. So ultimately, unfortunately, you cannot solve each of these 4 equations separately. You have to solve the whole system at once. That's what we mean by coupled. In general, yes, I mean there might be situations whereby, you know, sheer luck, or maybe very good choice of coordinates or coordinate system, one of the equations decouples and you can solve it separately, then you end up with 3 coupled differential equations of 17 terms. It's a difficult system, so they're coupled. Finally, it's a nonlinear differential equation. And again, let me ask you if you have any idea what a nonlinear, what that means, mathematically speaking, for differential equations. It has all kinds of meanings in different contexts, but for differential equations.
It means it's not to the first order, the independent variable.
Yes.
Order.
Yes, agreed. So it means that the 4 variables that you're looking for are themselves raised to a higher power than 1. In fact, that happens here. Look, you have one of the things that you're looking for, and it's multiplied by one of the other ones. That is called nonlinear. Okay? Linear would mean if they only appear non-multiplied with themselves or with one of the other 3 variables. Unfortunately, nature has decided that this is how things go. So, beautiful sentence, 4 equations, equal values are coupled and they are nonlinear. This is a mathematical nightmare to solve this. Unfortunately, yes. I mean, you can get PhDs, yes, working out the details of these things. I speak from experience. So yeah, Einstein himself thought, well, you know, you can only find approximate solutions to these sorts of equations. But again, nature has decided that this is the way that it is done. Let's make things a little bit more clear. Suppose that you want to know how you go from this point A to point B. Okay. So point A and point B. Well, points on this sphere, do you remember what the coordinates are with which you can identify point A and or point B? You have this sphere, you need coordinates. What are typical coordinates that you would use for a sphere? Maybe this one, right? B, something like that? Would that work? Okay. Yes, in this particular case, if you are on the surface of the sphere, the R will be constant, I indeed. Yes. But generally speaking, if you have some very strange four-dimensional space-time, then you would have four of these. Time is in there as well. Now, we've neglected time until this point. Do you understand why we have to put it in? Can somebody give me a one-sentence argument?
Because we're working with contractions, we only apply
That's
to
true.
four vectors.
It's bent together with space, so it changes
Yes.
the same rate.
But, I mean, I'm happy with both answers, but one very quick answer would be, well, you're talking about general relativity, which is the more general case of special relativity, and already in special relativity, space and time cannot be separated from each other, yes? So this, of course, extends to general relativity as well. So you would have four of these things. So in our example here, our four vector would have four of these things. And here's where all these things show up, right? Because they are coupled. What does that mean? It means that if alpha in one of the contractions happens to be t, you would have a time coordinate here, agreed? But the beta could be either of these four. So apparently, in order to solve, suppose that you want to solve for time, mu is the time coordinate. Then this contraction will certainly probably contain time coordinate itself, but the beta contraction will also contain the other three parameters. So that means if you want to solve for time, you have to put in that you already know how r works and how theta works and how phi works. Now, okay, so we're going to look for how r works. So what do? We take the same equation and we look for its r version of this equation. But the same thing applies here. If you want to know how r works, because you need the solution to that one to solve the t equation, then this double contraction will probably contain r, but it will also contain theta and phi. So you need to know those. Again, it's a mess. It really is a big mess. And then, of course, there's nonlinearity. Now, you might know from your courses in differential equations, or maybe by osmosis from other courses where you have used differential equations. Nonlinear differential equations do not have a generic solution method. Linear ones do. The method might be difficult to apply in practice. You might get stuck, but there are tricks in linear differential equations where you can always find a solution. You know in advance how many solutions there are and how they are related to each other. There's all this whole body of work. Now you can prove from mathematics that if your differential equation is nonlinear, like these ones are, that there is no such general trick. What you will have, of course, is that there are solutions. It's just there's no standard trick to solve it. So that means every single time that you want to solve this set of four equations, you have to start from scratch. You have to find your own little ad hoc trick for that particular situation. So that sucks, right? It can get worse too, because this is just things that move under gravity. Suppose that something moves under gravity, but also under electrodynamics. Then you get extra term still, something that tells you something about the Maxwell tensor. For people who have done electrodynamics, it's the A mu term, right? So that thing comes into play. So it's a huge mess. That's the bad news. Here's some good news. How easy or difficult it is depends on this object here. That thing I'm going to call the Christoffel symbol from now on, and in some texts you will also hear it as the connection. Now there is a slight difference between the Christoffel symbol and the connection. We're not going to worry about that. I'm going to write out, again, I'm just skipping the mathematics for now, just telling you how this works, and then we're going to look into mathematics. I'm just going to tell you what this Christoffel symbol is. There we go. It's 1/2 times the metric tensor of your particular space-time. And I always need a small amount of puzzling before I get it right. This is correct. There it is. this thing is what we call the Christoffel symbol. Or, again, in some texts you will find it under the connection. Now, let's look at the thing for a moment. How many terms are in the Christoffel symbol? I mean, yes, there's 3, but you know there might be some more hidden in the contraction somewhere. Is there a contraction? If so, what index?
The new.
The new, okay.
Yeah.
So that means the new will, in principle, go through its 4 values, yes? Okay, so this contraction with that one, how many terms does that give you?
16.
This one and that one?
32.
Well, 4 for the contraction, but then 16 terms in total.
Well, I don't understand what you mean by in total.
Because you also have the alpha and the beta, which can take all different.
Oh no, that is very true. But suppose that I
Yeah,
fix
so
my
the
alpha and beta. Okay.
Then
And
it's
how many terms?
4 for
4,
each of them,
okay.
and then 3 times.
And that 3 times. So
So
this
12.
by itself is 12 terms. So I was lying when I said 17 terms. It's 17, 16 of which contain themselves 12 terms. Okay? Again, it's a mess. Now, I was promising you good news. This is not good news. I'm giving you more bad news. Here's the good news. If somebody has given you the metric tensor, you can calculate this thing. It might take you a while, because you know there's 4 alphas, 4 betas, and 4 of these mu's, so you have quite some possibilities there. But there is absolutely no principal difficulty in finding these things. You don't even have to solve a differential equation. You just take your metric tensor, put it in here, take a couple of derivatives, add everything together, you will end up with expressions for these Christoffel symbols, and then you're done. So getting a Christoffel symbol, that part is easy. Once you have a Christoffel symbols, you put them into this thing. Let's give that thing a name too. It's called the geodesic equation. And then you end up with your differential equations that you have to solve, the 4 sets. So general relativity in practice, to use it is actually, well, not really that hard. If you have found, just as we did last week, what the metric tensor is of curved space-time, so you have this thing, you can calculate the Christoffel symbols, you put them in here, you solve that system, and then you know how things move in that particular curved space-time. That's a series of steps that we have to go through. It's just a lot of work. Now, usually people use computer programs to calculate the Christoffels. You can also do it by hand. We will do it by hand. The good news is the metric tensors that we're going to look at, the black hole one and the gravitational wave one and these sorts of things, are fortunately easy enough that you can do it by hand. In fact, all these terms that you have here, the 12 or whatever it is, they're really not that many usually. Why? Well, first of all, your metric tensor itself, as we've seen a couple of occasions, contains many zeros, right? So that means many of these terms are just simply 0. That's one. Secondly, note that what this thing requires you to do is take derivatives of the metric tensor. So even if the metric tensor in some component is not 0, but is a constant, it will still vanish. So generally, you don't have to worry too much about these things. In fact, let us, right here, right now, calculate immediately all the Christoffel symbols for Minkowski space-time. So we're going to go to special relativity. We are in an inertial system. We've done our first law of Newton check. We now know this is an inertial system. There's no other force around, no gravity, no curvature. Do you remember what the metric tensor looks like for a Minkowski space-time?
Just a unity.
So 1, 1, 1, 1?
With a minus.
With a minus sign, right? This is special relativity. The time part always comes with a relative minus sign. Okay. You've seen this in special relativity. This is the metric tensor for Minkowski space-time, or if you want, in an inertial system. We even have a special name in special relativity. We call this particular metric tensor eta mu mu. Good. Now, can somebody already at a glance tell me what Christoffel symbols are going to be?
0.
So this thing leads us to Christoffels, yes?
So 0.
0? I hear a 0.
Yeah.
More people 0. Nobody wants to put 1 in somewhere, or -1 or 15 or pi or tangents or logarithms. Nothing, no? All zeros? Why?
Because of the derivative and because of the zeros.
These are all constants, right? If you take derivatives, you will get constants. Okay, so all of them, for every alpha, beta, and mu, you will get 0. Yes?
Does that hold for every flat space-time? So,
No.
god damn it.
Yeah, I know. I know, that's so sucky, because what we also looked at last week was that we had a flat space-time. Well, we talked about flat space, but let's put time back in, okay? What we looked at last week was that if you have a flat space-time, you can still write it in spherical coordinates, right? And then the metric tensor all of a sudden looks a little bit different, because all of a sudden you get an r somewhere, or an r squared, and a sine squared theta, or something like that. And that means that all of a sudden in a still flat space-time, a Minkowski space-time, just written in spherical coordinates, your metric tensor will not contain numbers, and the derivative will not be 0. So that means that even if you are in a flat space-time, you might still end up with Christoffels that are non-zero.
Okay, so that's a bit of a different question, I suppose, but how do you even derive a metric tensor? Because I
Yes.
just assumed that if you were in spherical space-time, because where
Yes.
you have the sine theta, it's...
That's certainly how we did it until now. I mean, how do you get a metric tensor to begin with? Last week we did it by saying we know what the curvature looks like, and we're just going to look for the metric tensor that describes it, yes? By taking a very small triangle and do the x squared plus dy squared plus dz squared and such. Yeah, that is the next question. I mean, where do you get the metric tensor from? There's a separate equation that tells you where the metric tensor comes from. That's this famous Einstein field equation. Maybe just for completeness write it down, and then I'll go back to here, okay? So don't worry too much about the equation we're going to write down now, but it's just answering Felix's question. Where do you get your metric tensor from?
Well, it's not that, like, my question isn't that much about where we get it from, more how do we take the derivative of a tensor?
You're not taking the derivative of the whole tensor. For every mu and beta, it is just a number or a function.
Oh,
It's a collection
yeah.
of numbers and functions, and for each of these numbers and functions you can take derivatives.
But if you take the derivative in terms of what do you have to...
Well, it says the first index
this one.
tells you.
That tells you what derivative you're going to take. This alpha, when alpha has t,
Okay, yeah.
you're going to take the time derivative of this metric tensor, which has 16 components. Which component will the new beta?
Alright, no,
component?
that makes perfect sense now.
Alright,
Yeah.
so where do you get your metric tensor from? Again, don't worry too much about it for now. There is a separate equation that tells you where the metric tensor itself comes from. That's this equation. Again, with all kinds of extra new symbols in there, which are unfortunately many, many terms still. Okay? This is the Einstein field equation. And since we brought it up, might as well give a small introduction to it, but very small only. This equation tells you how you curve space-time. This equation at this side has something T mu nu, which itself is a tensor. It's called the energy momentum tensor. It tells you how much energy or mass or momentum there is in a particular region of space and time. If you know what that is, for instance, I could take all of your masses and how much motion and heat there is, that gives you the total amount of energy in this room, per location, per time. That is all encapsulated in this thing. If I put it in here, I can solve for the left-hand side, and then the left-hand side will spit out the metric tensor that agrees with that amount of mass and energy and heat and these sorts of things. So your metric tensor you get from knowing how much energy there is in a particular region of space and time. Once you have your metric tensor that's being spit out by that equation, you use it to calculate Christoffels, you put it in there, and then you know how things move in that space-time. That really is the whole body of general relativity. Okay? Application is hard. Now, going back to my example here. In a Minkowski space-time in x, y, z, and t coordinates, you can immediately see, well, wait a minute, all my Christoffels are 0. Okay? Let's use that to immediately give an interpretation to that thing, the geodesic equation. Because what will that equation now look like? If we're going to look for motion in a Minkowski space-time in x, y, and z coordinates. Tell me, what does the equation reduce to?
For velocity
Almost?
squared.
Not squared?
Like the acceleration is 0.
For acceleration.
Well, first of all, you see that the whole stuff with the Christoffels, all of them vanish, yes? So the geodesic equation, in case of Minkowski space-time, reduces to this thing. Now, here a couple of people say, wait, I sort of see a velocity in there. That's true. A first derivative of the four coordinates with respect to proper time is what in special relativity you call a fourth velocity. But you're taking a second derivative. We call that an acceleration. Now, just as you would have an acceleration in Newtonian physics, that means look how much meters somebody is moving and take twice the derivative with respect to time. This is sort of like a bastard object. Do you remember the discussion that we had on fourth velocity that I sort of called it a bastard object? Do you know what it meant by that?
Because the x from one is from the inertial frame and you use it proper
Exactly,
time, so
exactly.
kind
So we're taking the amount of distance, dx, as seen by me, and we take the derivative with respect to that thing that is moving, that thing's time. So you're taking a certain amount of distance and take derivative with respect to some other coordinate frame's time. So in that sense, it's a bastard object. Okay. Now, you can do these derivatives twice, so you get something that you would call the proper acceleration. It is 0 in this case. Now, if you have an acceleration that is 0, what does that mean about motion?
Constant velocity.
It's a constant velocity. And to be very specific, it's constant proper velocity in this case. Agreed? So, from this you can immediately tell that dx d tau and dy d tau and dz d tau, all of these have 0 constant velocities. Excuse me, are constants. Yes. The accelerations are 0, the things themselves are constant. Okay, they're constant. What does it mean about the shape of the path that thing is following? If all its 3 velocities in space are constant. That's a straight line. We have recovered Newton's first law here. Do you see that? Apparently, if you are in an uncurved space-time, should be a little bit more clear in my phrasing here. By uncurved, I mean that time itself is allowed its little special minus sign, okay? Minkowski space-time. In a Minkowski space-time, apparently things move in a straight line with constant velocity. That's what you see here. You see something else as well. As you know, you can have 4 parameters, and I've only listed 3 of them. There's another one. This is constant. What does that mean? dt d tau is constant. My time versus the other guy's time is a constant, their derivative. What does that mean?
The time dilation doesn't change.
Exactly. It's a fixed time dilation. You might even remember that this thing in special relativity we call gamma. And if gamma is constant, that means that apparently there is constant velocity between the two of us. Exactly as you would expect with the Minkowski space-time, right? So, what you see here is that the geodesic equation is really the generalization of what you already knew from special relativity. We just refined Newton's first law. Now, this should not be very surprising, because as you recall, an inertia frame is defined as a system in which Newton's first law holds. So of course we're going to get it out. But it's good to see that everything is consistent. Now, the beautiful part happens at the moment that we are in a curved space-time such that these are not 0. We see many examples last week where you have a curved space-time that has a particular metric tensor of which the derivatives are not 0. Then you will find that the second derivative of these 4 coordinates is equal to something something. Does that remind you maybe of a law, maybe from classical mechanics? The second derivative, an acceleration is equal to something. Maybe there's a Newton's law that reminds you of this. Okay. In case you are in a situation where, here we go. In case you are in a situation where space-time is curved, really curved, in the sense that you get non-zero Christoffel symbols, then these equations will, this very trivial rewriting that I'm going to do now, are going to give you second acceleration is not zero. Yes? This is Newton's second law. It tells you that if you are in a curved space-time, apparently you do not follow straight lines. You do not go with the constant velocity. Generally, you're going to be shifted in particular ways. Is that surprising? Well, you can tell by the tone of my voice that I hope that the answer is no, but maybe you can connect it to what we talked about last week on Tuesday. What happens if you go to a non-inertial system? You feel fictitious forces. So this part here is the amount of fictitious force that you feel when you go to a non-inertial frame. That's what this thing tells you. Now, I'm not saying that the Christoffel symbol itself is a fictitious force. I mean, you need the whole body of the thing, right, including the two derivatives. But this whole thing by itself apparently is a measure of the fictitious forceness that you encounter when you go to a non-inertial frame. Claim. That is also the amount of gravity that you feel in that particular curved space-time. Do you agree with that? That was the whole thing that we discussed last week, that fictitious forces are indistinguishable, equivalence principle, from gravity. So this thing is what gravity is in general relativity. Do you see that we're now really connecting things to each other now? The curved space-timeliness, the metric tensor, and this idea that you should feel gravity in a non-inertial frame. I promise you we're going to connect these things to each other. This is the connection. Well, in fact, that's the connection. Again, I don't know if it's called a connection for that reason, but that's the idea. Any questions so far? Because I haven't told you where the equation comes from yet. Just tell you what it says. Everybody fine? Okay. Note that the Christoffel symbol only depends on the metric tensor, right? If you have your metric tensor, somebody told you how space-time is curved, you can calculate the Christoffel symbols, and thus you know how much gravity and or fictitious forces you feel. So apparently what we see here, just from the mathematics alone, the fact that this Christoffel symbol only depends on the metric tensor, is just another way of saying that all of your gravity is encapsulated in your metric tensor. That's the only thing you need to calculate the amount of deviation from a straight line. And the metric tensor, as you know since last week, is a measure of your curvature of your space-time. So this is really connecting everything together. I promise you that the curvature of space-time is a direct measure of your gravity, and here's where you see. If you know how your space-time is curved, you know your metric tensor, you know your Christoffel symbols, and thus you know how much gravity you feel. That's everything. That's the whole story. It's not that hard, is it? Yes?
Is it also the case that if you then multiply both sides with mass that you get forces?
Yes. Here's a good question. Why doesn't mass enter in the first place?
It's independent of the mass, the acceleration.
Exactly. We saw on the gravity things fall in exactly the same way, regardless of what mass is. Agreed? Mm-hmm. So of course you expect mass not to be in there. Now when Einstein found this equation, the only thing he had to do was find out how do you get this metric tensor. This goes back to Felix's question. Where you get the metric tensor from. And I'm not going to give a full derivation here now. I'm just going to give you a couple of snippets, and in a couple of weeks I'll tell you something more about the equation. But we're so close, it's low-hanging fruit. Let's say a couple of things about this. What produces gravity in Newtonian physics? Mass. So, Einstein knew that if you want to have some equation that tells you the metric tensor, because the metric tensor ultimately gives you gravity, or the force of gravity, then apparently what you're going to need is some equation that relates mass to this metric tensor. And then Einstein went out and to see if he could find that equation. Ultimately he found this one, the Einstein field equation. I already told you that this T mu nu here contains all the masses and energies in the universe, in particular region of space and time, and then the other side tells you the metric tensor. So he knew that on the left-hand side there should be something that is only dependent on the metric tensor, and the right-hand side can only depend on masses and energies. He just had to find the right way to connect these things together. exactly how. Why is there 1/2 here? Why is it 1? Why isn't it 1/8? And this number here, why is it 8 pi g over c to the 4? Now, the trick that Einstein used was that he knew, wait a minute, I know that if things move slow enough, and if gravity is not strong enough, I should get back by Newtonian gravity, right? This equation should give me back ultimately this, the Newtonian version. And then I should make this a normality, not a property. So, what he had to do, he knew that if this equation has to be such that if you make things such that they don't move too fast, so this proper time becomes a normal time, and if gravity is not strong enough, then this equation, or that equation, should ultimately give you this. And that was enough for him to find that this number should be 1/2 and this number should be such. The g comes in there directly because it had to reduce back to Newtonian gravity. So he knew what in the weak gravity and the small velocity limit that equation should give you, and that was enough for him to fix these constants. I'm lying a little bit, because he needed a little bit extra. 2 more ingredients. We fix these numbers now based on the idea that it should give you back Newtonian gravity. I haven't told you why it looks this particular way. There's this thing here, Gesundheit. There's this thing here, R mu nu, it's called the Ricci tensor, which itself is a very difficult combination of the metric tensors. I'm not going to write it out, it's too much. But why is it that the equation has this particular combination of this tensor and then the metric tensor and this other R thingy? Where does that come from? 2 more ingredients, I told you. One of them is he knew that energy should be conserved. Now, if you have some energy here, because this ultimately gives you the amount of energy, that means if you take its derivative, it should give you 0. Now, if you know that energy should be conserved on the right-hand side of this equation, it should also be conserved on the left-hand side of the equation. That fixes how these things are related to each other. That's one ingredient. The second ingredient that he had to put in was it's a little abstract, but let me try anyway. That he should only have second derivatives of the metric tensor in there. Now, it's hard to tell because I haven't really told you what these r's are, but these r's, this one and that one, are themselves derivatives of the Christoffel symbol. Okay? If you take a derivative of the Christoffel symbol, you get second derivatives of your metric tensor. Now, there was a very strong reason for him to know that you should have some expression of curvature spacetime that can only depend on second derivatives and not first derivatives. And I'm hoping, well, it's abstract, but maybe somebody can sort of feel why first derivatives of the metric tensor should not enter in your curvature of spacetime equations. Maybe you can think of a reason. How do you get curvature? If you're in an inertial system and you want to go into some gravity field, what do? You stay in your inertial system, or you do something else?
Non-inertial system.
You go to a non-inertial system, right? You don't go to another inertial system. You just go to some coordinate system that accelerates with respect to your original one. Agreed? How many derivatives do you need to get an acceleration?
2.
That's 2. So Einstein knew that the left-hand side of the equation should be such that particular combination of the metric tensor that itself has a 0 derivative to get a conservation of energy, and that it should, at the very least, at the lowest derivatives should be second derivatives, because that's how you go to curved space-time. Those ingredients, so we have listed 3 now: second derivatives, conservation of energy, and lastly that it should reduce to Newtonian gravity. That was enough to fix this equation. That's how I got that one. Now the rest is mathematics, the details, okay? But can you see how much sheer physical insight he put in? Now Einstein was a smart man. The idea for this he had, I think, in 1908 or something like that. He published his paper in 1915. That's how long it took for him to have these 3 ingredients and get the right equation out. Small anecdote. Einstein was very close to finding the final expression. I mean, if you ever have the time, read this beautiful biography by Walter Isaacson on Einstein's life. There's this beautiful chapter on when Einstein was in the last phase of finding this Einstein field equation. He had the unfortunate event that he went to his friend, Poincaré, and he said, look, Poincaré, I'm working on this, and it should be such and such and such and such. And Poincaré himself was a very smart mathematician. So Poincaré said, I know what Einstein's objective is now, let me try myself. So we're having this little Cold War, who found the equation first? And Poincaré came up with one solution, and Einstein came up with the other one, and it turned out that Einstein had the correct one. Otherwise, these will be called the Poincaré solution or something like the Poincaré equation. So just as a little moment of warning, be careful if you're on the way to finding something important. Do not tell your friends, okay? Not try to steal your thunder here. But Einstein found it, and he published it in 4 papers. Small extra historical anecdote, and then I'm going to tell you where this equation comes from in the first place, the Diodesky equation. The first thing that Einstein applied it to was a long outstanding problem about the motion of Mercury around the sun. If you use usual standard Newtonian physics that you have learned in high school, and you apply it, and I'm sure that Ronald has maybe done this with you in your mechanics course, and you apply it to the motion of planets around the sun, and you do not limit yourself to circles, okay? Circles you know in high school, but the real ellipses, Kepler's laws, you derive them from Newtonian gravitational physics, you will find that the planets move with this velocity at this distance, right? You have your 3 Kepler laws. Specifically, Kepler's second law tells you how fast a planet instantaneously is moving given how far away it is from the sun. The closer it is, the faster it will go. The further away it is, the slower it will go, and that will give you your ellipse if you work out the details. Now, if you calculate that number for the planet Mercury, you will find a particular number, right? How fast it should go, or therefore how many seconds it takes for the thing to make one revolution around the sun. But if you measure how fast Mercury is going, you will find that Mercury goes a little bit faster than Newtonian physics says that it should. It's a ridiculously small number. It's 43, it's a famous number in relativity. It's 43 arc seconds per century. So that means that if you would take the amount of sky, that's 360 degrees, right? You take 1 degree of that, and you take that, you divide it by 60, you get an arc minute. You divide that one by another 60, you get an arc second. So there's a very small amount of angle on the sky. Per century, Mercury goes 43 of those arc seconds per century faster than Newtonian physics says that it would. It's a ridiculously small number. And this problem had been known long before Einstein came around. It had been known by astronomers because people had been looking at Mercury for, I don't know, centuries and centuries, so people had lots and lots of data. And people just thought, well, it's probably some anomaly, or maybe something wrong with the measurement, or even people who thought maybe there's another planet somewhere closer to Mercury that's pulling on it, making it go a little bit faster. Right? They call it Vulcan for the Star Trek-minded people. Never found the planet. Einstein, when he found this equation, he applied it to the solar system, right? It should give you something Newtonian, probably plus a little bit extra. The little bit extra he calculated for Mercury, that was 43 arc seconds per century. That's what he found. He wasn't looking for that number. In fact, if you recall, when I told you this 1/2 and where these numbers came from, it had nothing to do with experimental data. Right? It was just based on the idea that energy should be conserved, should be second derivatives, and it should give you back Newtonian physics if you look at things that move slowly, like planets. So that means that these numbers, the full equation was completely fixed. There was no numbers that you can adapt and make sure that it will fit experimental data. So it was all or nothing for this equation, right? It either fit the data or didn't. So when he applied it to his first thing, Mercury, he found exactly 43 arc seconds per century. And there's a famous letter that Einstein then sent to his best friend, mathematician called, I think, Michael Besso, something like that. That Einstein wrote that he literally got heart palpitations when he had calculated that number, when he found that number came out. And that he had to lie down because he was afraid that something might happen to his health. Because he knew that he had really, this was an ultimate test, okay? So if you read Einstein's original papers from the winter of 1915, this is, he had 4 papers in which he showed all of this. In his final paper, he showed the Mercury theory. And you showed the 43 arc seconds per century. So that was a huge triumph, agreed? I mean, it's beautiful. Now, ever since we've been using this equation, now all of this is all based on the idea that we know where this comes from. I'm not going to go through the full mathematics. I wouldn't say it's particularly difficult, but I think that this is something we're going to do in this tutorial. Right? It's good practice in contraction, so I'm just going to tell you the gist of it, how it's done. And it has to do with the following. Do you remember? Right, so we know our equations now. Let's give a little bit of mathematical background here. Do you guys remember that if you want to calculate how much distance something travels from one point to the next on a curved space-time, what we did was we split up that curved space-time in very, very, very small little stretches of distance. For each we assumed that it was Euclidean, and then we just integrated all the small patches together and we got the total amount of distance. Okay. Now, if you make a curved space-time ridiculously small, just as we did when we calculated metric tensors, what path will things take on a very small,
Straight.
A straight line, agreed? So what you would expect is that if you make a curved space-time ridiculously small, you zoom in a little bit more. In fact, that's exactly what we did in the tutorials. You get Euclidean space, or let's put time in. You get Minkowski space-time. But we know how in Minkowski space-time things move, right? In a straight line. Now, if you go in this particular small patch of Minkowski space-time, and you go from one point to the next, well, it's a straight line, but there's if I were to ask you to state that straight line, but now in terms of time. So if you want to go from here, well, let's take one of you. You know, I'm going to walk towards you. You might say, you know what, I'm going to do it in a straight line. That's fine. That's what Newtonian physics would tell me that I would do. In terms of time, what will be an equivalent statement? Let me demonstrate here. I'm going to walk towards him. This is option 1.
The minimum amount of time?
The minimum amount of time? Okay. Is that true? Well, again, demonstration. No, straight line. Okay. Option number 2. I'll be back. I'll be back still. All right. There we go. That's certainly a way to get to him, okay? Not a straight line. You're right. Also not the shortest amount of time. Newton's first law you can equivalently state as nature looks for the path of the least amount of time to get there. That's Newton's first law. In absence of gravity, or if you will, in a very small patch of space-time, things will move in a straight line. It's another way of saying it will move in the shortest amount of time. How do you go from point A to point B in Minkowski space-time? Such that the amount of time that it takes is the shortest. Now,
wait, can I ask a question?
Of course.
Because like in quantum mechanics, all that shit goes out the window, right? And if you, well, if you you say you zoom into really small pieces of space-time, well then you get things like the Planck length and Planck time. And that,
yes.
Like, how does this make sense then?
It doesn't.
Okay.
No, I mean that's not a dismissive answer. It really is. People do not know how to incorporate these ideas into ridiculously small amounts of time, or small amounts of space.
So we are talking about theoretical time and theoretical space.
Yes. So in the sense that if you're going to ignore what happens that you're going to ignore Planck effects on a very small scale. By the way, you don't even have to go to Planck length. You only have to go to smaller than quantum length. That alone is enough to see the first quantum mechanical effects.
Okay.
So, in fact, what is a straight line in the first place if things do not have a specific position at any moment in time, because Heisenberg forbids it. Yes. So there are certainly ways that this cannot be immediately applied to quantum mechanics. But then again, mathematically speaking, you can just pretend that if it goes small enough that it goes straight line, you just ignore the quantum mechanical effects. But quantum mechanics and relativity, as you can already see here, have huge problems with each other. So, for that reason, I'm leaving quantum mechanics out, just like Einstein did, by the way. But we see this, yes? We're going to split up our curved space-time into very small patches. We already knew that every small patch, by very good approximation, leaving quantum effects out, is itself a little piece of Minkowski space-time. And in little piece of Minkowski space-time, things move with a constant velocity in a straight line, or equivalent statement, such that it has the least amount of time that it passes. Now, up till now, when we were talking about small amounts of distance in a curved space-time, we wrote it as such. Yes? Where mu and nu typically in our examples of last week either were 2 coordinates, theta 5 for instance if you were on the sphere, or maybe 3, maybe an r was either x, y, z or something like that. But we are in space-time now. We're going to put the time back in. Special relativity. Remember, either your courses in special relativity or our first lecture would have something like this. Do you remember this expression? Yes? Do you remember what this means? D tau. And then a physical interpretation. I'm leaning on your special relativity knowledge right now.
The change of time that an observer perceives.
Property.
Yeah,
But
proper
the name is
time.
proper time. What does it mean? It's important for our discussion. What does proper time mean? D tau is proper time. Agreed. What does it mean?
The 2 events happen at the same location.
It's the amount of time for the observer who sees 2 events happen at the same location. That could be the motion of the observer himself. Yes. If an observer begins here, that's event number 1, and a moment later he is over here. In his own coordinate frame, the 2 events happen at the same location, right? That's what happens if you drag along your own coordinate frame. Then the amount of time that that guy measures on his watch between here and there, that is what we call a proper time. Now, just to be really sure that you remember this from your special relativity course, if you would write out this contraction, you would get your famous this expression, right? And you also know that if 2 events, the 2 events being you here and in a moment later being over there, that means that those 2 events for you happen at the same location, so dx is 0, dy is 0, dz is 0. So this, for that particular observer, becomes dt, and dt is the amount of time that he measures. So d tau, if you recall, is the amount of time that passes for the observer who himself is moving. Okay?
And that is proper time, right?
That is proper time, yes, by definition, yes. And last year there was somebody, one of our French students, who actually knew why it's called proper, because it's some mistranslation from the French word proper. Which
Proper means your own
yeah,
time.
it means cleans, I know, but does it also mean your own? I mean,
Yeah, it does.
Yeah.
Well, let's
Which,
ask
yeah,
the native
it does,
speaker. Does it, yeah?
So
Okay, it's really your own time. All right, so. We're going to do away with the s squared at this moment. We're going to write everything in terms of d tau squared. D tau squared in a curved space-time is literally just this expression, except that you have to put your curved space-time metric in there. This is literally what we did last week. We wrote down the amount of distance last week in terms of the metric tensor of that particular curved space-time. The only thing that I did was I put time back in because we left it out last week. And I'm now writing everything in terms of the notation that we did in special relativity. Okay? Hence the minus sign. So, we already saw that this number has to be smallest. Agreed? You're going to split up your curved space-time in little small patches, and each of these small patches, this number has to be smallest because it travels in a straight line in every small patch. So the total amount of time, let's call it d tau, the total amount of proper time, is this expression. We are now in a mathematical situation, namely we understand from from Newton's first law perspective that this number should be minimized. How do things fall in a curved space-time? In such a way that in every little patch, the amount of time is smallest, so that means the total amount of time should be smallest. Delta tau, big delta tau, over the whole curved space-time from point A to point B should take the smallest amount of proper time. Yes?
Well, this might not be the smartest question, but if you integrate d tau,
Yes.
why do you end up with delta tau? Wouldn't you just end up with tau?
That's just a matter of...
Okay, so the delta tau is not the change in tau in sense of differential.
It is a change in tau.
Okay.
But usually what people do is that they take the starting point of tau
That's
to be
zero.
0.
Okay, so
And,
all right,
and
that
you
makes
could,
sense.
I mean, that's fine too. I mean, it's just notation. As long as you understand that this number just means the total amount that somebody experiences as he goes from point A to point B in a curved space-time, that amount of time.
Okay, no,
Okay.
that's not good.
Now, this number should be minimized. Minimized. Nature chooses the path on a curved space-time that takes the least amount of proper time. That's the argumentation here. In the book, Hartold, this is called the Variational Principle. So you might have come across that word. But this is the physics behind that. Every patch, things go in a straight line, therefore smallest amount of proper time per patch. So the total amount of per patches should give you the total, the minimum amount of proper time. Here's a mathematical question. The number that comes out of this integration depends. X mu is now the path that you take through this curved space. It's the location of the thing that's moving through the curved space. Depends on tau. For every function x mu that I put, this integration will end up with a different number. Right? It's just first dimensional or one-dimensional calculus from your first year. If you have f x dx from point 4 to point 5, I ask you what the outcome is. It's a number. Well, what the number is depends on what f is, agreed? If I take x to be fx to be x squared, I get a different number than if I take fx to be the logarithm of x. Now we know from our physics that these four functions should be such that the outcome of this particular integration is the smallest number possible. So for every single set of four functions that you put in here, you will get a different number. Which one does nature choose? The one that gives you the smallest amount of proper time. That's a mathematical question. What path is that? Of all the possible four functions that you can choose for x mu, which one is it that makes this one smallest? The answer is on the board. This is me pointing. It's the x that obeys this equation. That's where the geodesic equation comes from. How do we know how things move on a curved space-time? They move such that their proper time is the smallest, and that means they move such that this particular integral has the smallest outcome. I'm waiting maybe for somebody from special relativity to say, I've seen this before. Integrals that should be minimized. I know this is period 2, so it's way, way back, right?
Least action
Yes,
principle?
Yeah.
least action.
Lagrangians.
Yes, Lagrangians. Yes. We had a similar situation there. We were looking at this principle of least action. The idea, in fact, I'm just checking right now. I think everybody was there, right? During that course. Except Felix and Cornel. Now, in special relativity, we had a similar situation. We introduced a new type of doing mechanics. That we said we had this thing we call the action. And the action, nature chooses the path that makes the action either minimized or maximized. There was a similar situation as we had here. It's just a matter of finding the right function. Yes?
Why would it maximize action?
Yeah, well, because ultimately I mean, the way that I build it up, I use minimized, because that's what it does. But it turns out that that equation that we have over there that solves your problem is also the solution for the maximum amount of time. It's like doing this. If I give you a function and I ask where its minimum is,
yeah,
you say I take its derivative and set it to 0, but that also gives you the maximum.
That makes sense.
That's the same here. I'm saying this should be minimized. That gives you that equation, but that equation also gives you the maximum amount of proper time.
And how is the maximum amount of proper time interpreted then?
Well, the good thing is that if you find a minimum amount of proper time, let me rephrase. There is no maximum amount of proper time.
Okay.
No, that's a good question. Because look, his question is, okay, if you're going to solve that and it gives you the minimum amount of proper time, what if you accidentally find the maximum amount of proper time? Right? That's not the one that you're looking for. Now my answer is, fortunately, there is no maximum amount of proper time.
So
can you see why that is?
Yeah, things can move forever, right?
Yeah, I mean,
if you don't take the shortest path, there is no
exactly. That's exactly the point. Let's visualize it one more time, okay?
No, I mean that makes perfect sense.
Okay.
I was just wondering because you said,
That
well,
was a super question.
we find maxima, so I assumed there would be none. That's why I was. Okay.
No, the question is just super good. It's just I like visualizing things, so I'm going to take it and run with it. So I'm going to walk to Cornel here. Yes. Okay, that's the minimum amount of time. Okay. Right. Now I'm going to take the maximum amount of time to walk from here to there. Okay. Oh, you know where this is going. Okay. Not done yet. Having too much fun here. Okay. I'm still not done though. Now, how long can I keep on walking, right? Forever. So if you have found an extremum, it necessarily in this context must be the minimum.
Okay.
Good. Now, how to get from here to there, that's a lot of contractions. And that's what I want to do with you on Friday. Now, just for people who might already want to look a little bit into it, do you remember, just as a small piece of jogging your memory, going back to special relativity. Remember this equation? Lagrangian integrated over all time, you want to minimize it. There was a particular expression that tells you what x and v should be in order to make this outcome s minimal. Now, I'm not going to blame you for not knowing this by heart, but this was the equation. You might even remember what the name is. It's the Euler-Lagrange equation. Why this particular equation minimizes this integration, we did in a tutorial for special relativity. You can easily look it up. It's still on my YouTube channel somewhere. Okay, right. So I'll probably see some views going up over the weekend, next couple of days. We derived this equation from the objective that this should be minimized. Here, there is also an Euler-Lagrange equation. It's just somewhat more complicated, and that's because this thing in the middle, if you want, you could call this your Lagrangian, right? That's the thing that you're integrating over. In fact, let's make it even more explicit. Let's put a detail outside and a detail here. It's mathematically allowed what I just did. It's now an integration over tau. It now looks very much like this, agreed? It's an integration of something over time. Sure, this is normal time, that's proper time, but the mathematical structure is the same. So this then...
Don't you want a detail squared inside?
Yeah, but I distributed the squared over the two derivatives.
Okay.
So there is your square, it's just over two derivatives. So if you want to make the analogy complete, this is now your Lagrangian, this square root. Well, if this equation and that equation are mathematically just the same thing, you would expect that the condition that minimizes it should also be similar, yes? So you might guess that this one is minimized in somewhat the same way. What is it? DLDO. We're already running into trouble. Look, I'm just trying to copy this equation to there. Do you see where the trouble lies?
You have to do it for each
Well, yeah, I mean, you have, there's not just one x, you have 4 now. T, x, y, and z, or T, r, theta, phi. You're stuck with that. Now, the other side, how about that? So, ddt, that would be d tau, right? You can sort of tell by analogy, but if you go through the mathematics, you will find this. And then you have to take another derivative of v. What the hell is v in this context? That will be the proper velocity, so that will be, just for which one? Because we have 4 of them.
Can't you just index them again as a 4 vector?
So
Also
something like
before,
this?
like x mu and
Something like that? Would that work?
Yeah.
Okay, that works. Okay. Now, we're sort of, smuggling here, right? We just assume that whatever it says here, that probably is here. We just replace a couple of t's by taus and a couple of x's by x mu's and such. You have to be a little bit careful here, right? So, but it is mathematically true. If you go through the full derivation, you will find that this indeed minimizes. But now comes the hard part. Again, tutorial. We have to take RL, which is this whole square root, put it in here, work out the result. But one thing you can already tell, because you're going to take a derivative of this thing. So you're going to find some expression that will contain derivatives of, at the very least, geometric tensor. Agreed? Those are the Christoffels. What you will also find is that you're going to take a derivative, a time derivative, of these things. That will give you a second time derivative. It's going to be that one. Rest of mathematics. That's a lot of contractions. I can already tell you that will happen, okay? But this is for Friday. All right. So, to wrap up, how do things move in a curved space-time? You have your space-time. You might have gotten it from your Einstein field equation. You might have gotten it from, I don't know, whatever the source, maybe divine intervention or something like that, maybe from some stone tablets in the cave somewhere, somebody gave you a metric tensor. Then you know that on that particular curved space and time, things will look for the path of the smallest proper time. That's how nature decides that things should move. What is that path? That's this one. How is it minimized by this equation? That means the geodesic equation. So, take your stone tablet metric tensor, calculate the Christoffels, put it back in here, and you get your 4 equations. You still have to solve the 4 equations, right? You still don't have your x mu as a function of tau, you just have the equations that they have to obey. But from that moment on, you can solve it. Very complicated, 17, terms, 4 equations, blah, blah, coupled. Fortunately, that was the good news that I promised. Our metric tensors are going to be simple enough that we can do this by hand. And we're actually going to solve how things move. Next week onwards, first example, black holes. So I'm going to give you the metric tensor for a black hole. And then literally we're going to calculate how things move close to a black hole, that they plunge in and never come out, and the time goes and stands still, and these sorts of things. Okay, any questions? None? Ridiculously crystal clear? Good. Okay. Let's have a break and then open question session for the midterm.